Good evening and namaste everyone. I am Bardhan Jangi from Nepal Hydropower Association. We generally do a webinar once a month in the energy forum of this association. So for this month, we have Bill Kappel here, and the topic of the webinar is probable maximum precipitation. What is it? How do we calculate it? How do we apply it? So, Bill Kappel is a president and a chief meteorologist of Applied Weather Associates. And you will provide a detailed discussion about the probable maximum precipitation. Bill, you can continue your presentation from here.
Thank you very much, and appreciate everybody's time this evening in Nepal and this morning in the United States for joining. Thank you. As you mentioned, the webinar today, I will be talking about probable maximum precipitation and how we calculate it, where we are today, and where we're going in the future. So a couple of things as a background on this, as we look at the outline for today's webinar. Probable maximum precipitation has been used for a long time across many parts of the world, and there's many ways that it can be calculated and applied. So we're really going to get into detail on that and provide a lot of examples. And understanding where we've been in the world of probable maximum precipitation and how it's developed for dam safety and hydropower application and using for inflow design for critical infrastructure, and of course where we're going, what our next steps are, what we plan to apply. And of course that includes things like climate change and how do we account for changing climate, and how that should be considered when we're talking about a deterministic PMP. Of course, probable maximum precipitation is very important because it's used for design. So what are the benefits of these studies? And of course, how are they completed and what are some examples? So we'll talk through all of those aspects today. Couple things, first of all, on the history of probable maximum precipitation. In the United States, probable maximum precipitation first really came into play back in the early 1940s for a study that was done in the northern New England region, called Hydrometeorological Report 1. And at that time, it was called maximum probable precipitation. So the definition and name has certainly changed over time. In the United States, there's been a lot of work to cover the country in the 60s, 70s, and 80s. And then starting in the 1970s, the World Meteorological Organization produced its first manual for probable maximum precipitation, largely based on the work that was done in the US, and continued to update those documents in 1986 and 2009. Also, other parts of the world begin to do significant work, places like India and Nepal and Southeast Asia, also in Europe and Australia, and the Bureau of Meteorology there started to produce several documents that would produce probable maximum precipitation following a deterministic process and a storm-based process, as well as statistical methodologies. And then starting in about the mid-1990s, Applied Weather Associates, my company, we started doing probable maximum precipitation studies to update a lot of the work that had been done in different parts of the world and really bring in incremental improvements, update climatologies needed for different calculations, and really lately, last 10 years or so, begin to incorporate not only deterministic PMP, but also probability estimations related to annual exceedance probability and climate change assessments. So there's been a long history of this work through the years. And of course, the requirement is to be able to quantify rainfall inputs that are used for hydrologic and engineering design for hydropower dams and dam safety and nuclear safety and mining operations and so on, and try to quantify that information in a way that can be used for those designs and try to reduce uncertainty, reduce risk, make sure these designs are safe and effective and performing as needed. And so over this long history, there's been lots of improvements in time to increase the databases used for these processes and really hone in on the methodologies and make them as accurate as possible. From a definitional perspective, just for deterministic PMP, the current definition, which is still in flux and recently changing in some ways, which I'll get into in a second, is PMP should represent a theoretical upper limit of the most amount of rainfall that could occur over a given duration, over a given area size, at a given location. One caveat that's really important in the definition of PMP is that it represents a physically possible storm, one that could actually occur. So that's something that has to be taken into consideration when PMP is estimated and developed is that we do not want to combine inappropriately a series of conservatisms or processes that would actually never be able to co-occur in Mother Nature. We want to try to represent how the atmosphere works and how it would result in rainfall for a given area over a given duration over a given area size. Now, one thing that's really important is that definition is to develop a storm-based or hydrometeorological report process of a definition of a PMP. So it's a deterministic outcome. Other methodologies are certainly possible, like a Hirschfeld statistical methodology and so on, which is a different consideration. But all of them should be based on data and information specific to your site. But again, this is a deterministic process. So recently, in the United States, we've gotten together with subject matter experts in the realm of meteorology and climatology and climate change and added to this definition somewhat. And really all it's doing in this updated definition is adding the things I just talked about, which is a probabilistic aspect and a climate change consideration. So it's really the process of continuing to update the PMP methodologies and databases and include things that support the deterministic processes with a probability estimation and a consideration of climate change. Now, for AWA specifically, we have been doing probable maximum precipitation studies, like I said, for a long time. And we've been fortunate enough to be able to do this work all over the world in just about every type of climatological and meteorological setting that you can imagine. The exception, of course, we haven't had a chance to do anything yet in Southeast Asia, which would be amazing because, of course, Nepal is such a unique country in so many ways. And so much hydropower and dam construction is going on there that's very important that the probable maximum precipitation estimates are as accurate and reliable as possible and taking some of the unique characteristics that not only related to rainfall runoff flooding, but things like glacial outburst flooding and debris flows and other considerations like seismic activity and so on. But these studies around the world have generally followed the storm-based approach that I mentioned before, which is producing deterministic PMP depths, and have dealt with all types of situations from equatorial regions to mountainous areas in Alaska, British Columbia, and throughout the United States and South America, desert locations, high Arctic regions, very wet locations, and areas affected by monsoonal conditions and so on. So it's the point of that is that by doing all these studies all over the world, we have been able to test and validate the process of probable maximum precipitation development using the storm-based approach. You know, the storm-based approach in and of itself, of course, is based on available data, available observed extreme rainfall events, and the ability to maximize those events and move them around to your location of interest. And so obviously in some areas of the world, there's a lot more data to utilize than others, and that makes for a variety of outcomes in the PMP estimation process. But new technologies like satellite remote derived precipitation estimation starting in the 1980s, so we now have more than 40 years of record of that, and model gridded reanalysis data sets like ERA5 from the European Center for Medium Range Weather Forecasting provide valuable data sets that give us nearly global coverage of the information that we need to do these processes. Now, through time, of course, like most scientific processes, and PMP is no different, there's been a lot of improvement through time, right? Especially in the updating of the storm database. So understanding and quantifying how rainfall accumulates in time, space, and magnitude is critical to PMP development. We have to make a lot of assumptions in the process. There's a lot of uncertainty. So the more observed rainfall events that represent extreme rainfall and flood events that we have to analyze and put together in this process, the more powerful and the more accurate the outcomes will be. So always wanting to update those storm databases. That's a critical component for PMP development. Obviously, when we develop PMP, as I mentioned earlier in the definition, it should represent a physically possible event. And so we want to really analyze the storm types and the seasonality that are important for a given location. Obviously in Nepal, where you have the monsoonal system and you have thunderstorm events and you have strong seasonality, especially at higher elevations, it's really important that the PMP represents those characteristics in detail. And in areas where snowmelt is important, it's really important that that's captured, quantified accurately, and that the amount of snowmelt, when it occurs and how much occurs concurrently with rainfall is captured. And of course, that's a component that's often changing as we move into the future. The climatologies used to maximize and adjust storms, those should be continually updated so that they're representing an atmospheric process, an atmospheric system that's representative of the storm environments that we're dealing with as we go forward. And then, of course, frequency of rainfall events. Again, this is a very important factor for helping to quantify the uncertainty and the probability of occurrence, not only of PMP, but just of rainfall in general. But it's also just as important, once we have these values derived, the PMP depths derived, how do we distribute those depths in time and space? So if you think about, if you have 200 millimeters of rainfall in 24 hours, does that all fall in 1 hour? Or does it uniformly distribute over 24 hours? Or something in between, right? That makes a very big difference on the way that the rainfall runoff and flood transformation works and the way that the hydrology will play out. So it's very important that we have temporal patterns that represent the storms and the storm types in your region of interest. And of course, spatial patterns are very important too. If you think about Nepal and the topographical setting there and how influential the topography is on rainfall accumulation, not only rainfall magnitudes, but also spatial distributions in upwind mountainous areas versus downwind and valley versus ridges. Those spatial patterns are critical and should be represented appropriately in your PMP outputs during this process. The quantification of uncertainty is a big improvement over the last few years as well. There's been several papers written on this that we've published that describe the different inputs for PMP development and how we can quantify the range of variance in those inputs, whether it's storm selection, rainfall reconstruction, rainfall and storm maximization and adjustment, storm transposition limits, the assumptions of storm efficiency, and so on. All of those have their own range of uncertainty. And when you put them together, you can quantify that range of uncertainty around that best fit deterministic value, right? So you can see where your PMP estimate falls in with that range of uncertainty. We'll take a look at that later on in this presentation. Again, assessments of probability that extend all the way through PMP are very important. So now we can set an annual recurrence interval of PMP depths. Even though they're deterministically derived, we can see that they're appropriate. We want to determine if they're appropriately rare or not, and how that fits into the overall picture. And of course, the climate change aspect, as we mentioned, are these things changing through time? And if so, how and when? So as I mentioned, one of the most important aspects of the PMP process is to utilize storm events that have occurred that represent PMP level rainfall. So this particular map is just a database of all the storms that AWA has analyzed over the last 20 years globally that have been used in PMP development. And there's nearly 1,000 storms that we've analyzed over the last 25 years. And again, they extend in coverage to really focus on the areas where we've done our work so far, but others have analyzed storms in other parts of the world as well, especially in Australia and Southeast Asia and Europe. So this is AWA's database, but there's more storms out there to utilize. And so when you're doing a storm analysis and a probable maximum precipitation study, it's critical that you've identified the biggest rainfall events that have occurred in your region of interest and analyze them fully to get the information that you need for PMP development. That would include depth area duration tables and hyadographs and so on. So what I want to talk about is how we analyze these storm events and how we get the information we need for PMP development. The key is we use our system that's called a Storm Precipitation Analysis System, or SPAS. This was developed way back in the early 2000s, in 2002, and it was like most scientific processes, it was based on necessity. When we started doing these PMP studies, we needed to update the storm database, as I mentioned. And we needed to develop a process that produced depth area duration tables and hyadographs and hourly gridded rainfall so that we could combine that database with previously analyzed work in the region, in this case, the United States. And so when we did that, we developed that based on guidance from the World Meteorological Organization and National Weather Service and the U.S. Army Corps of Engineers on how they produced DADs in the past so we could produce them in a similar manner and have a consistent data set through time, but produce a process that utilized much more updated information like weather radar and satellite remote precipitation, climatological base map to spatially distribute rainfall between rain gauges and so on. So in that process, of course, we had to verify and validate the software to make sure that it did exactly what it was programmed to do. And to do that, we had to produce a storm called Pyramidville as a synthetic storm to test that answer. And that process has been honed over the years, as we've done this nearly 1,000 times over the last 20 years, again, all over the world, and just about every type of storm you can imagine, and every type of topographical and climatological situation. So that validation process, just real simply, took into account if we knew the exact answer of how rainfall was accumulating in time and space and through a synthetic storm, would the SPAS process exactly replicate that process and that output in our analytics? And of course, the answer was yes, because the methodology was derived following standard processes and produced DAD tables that exactly matched the known answer. So we were able to validate and verify our process. So we have two ways of doing this. One is without radar, where we just use observational data and spatially distributed precipitation, some climatological base maps and other types of information. And then a process where we can incorporate radar. So radar observed precipitation, which gives us a good set of information from a spatial and timing perspective to utilize. What does that look like, though, when we put all those pieces together? What are the outputs of SPAs that we're using for PMP development? Well, here's a storm that we analyzed in Malaysia and Indonesia several years back for a study that we had done in Papua New Guinea. And you'll notice the rainfall accumulation spatially, right? So we have our heaviest rainfall right over the southern Malaysian peninsula here, and we're talking about 400, 500, 600 millimeters of rainfall over a few day period. And we'll take a look at how this accumulated in time in just a second. But we also have rainfall accumulation, of course, over the water. It doesn't just happen over land. And so being able to incorporate satellite remote precipitation climatology allows us to look at how rainfall accumulates not over land, but also over water. Because when you put this information together into a depth, area, duration table, it includes all of the precipitation that occurred within this region of observation. And that becomes your volumetric consideration of rainfall. So it's important that we have observations covering the wide region. When we do these analysis, we can also look at the recurrence interval of that rainfall. This is from a hurricane or tropical cyclone that made landfall in South Carolina and North Carolina back in 2018, Hurricane Florence in this case. And all the areas that are in red here have a recurrence interval that's greater than 1 in 1,000 years. Right? So a very rare rainfall event, of course, which caused extensive flooding and damage and several dam incidents in this area of North Carolina when it occurred. So being able to quantify the rainfall from a pure magnitude perspective and spatially and from a frequency realm is very important to put those two pieces together. Now, for probable maximum precipitation development, what we need are the outputs that we can maximize and use and put into a gridded climatology and use for development. So SPAS, as a standard process, as I mentioned, produces depth, area, duration tables. So here we can see rainfall accumulation in time. These are hours on the x-axis. And in space, these are square kilometers on the y-axis. So we can come here and we can look at 24 hours at 100 square kilometers, and we can see that this particular storm, as observed, produced 321 millimeters of rainfall in 24 hours. Right? And so then we do that for all the storms used in a given study, and we can compare them to each other in time and space before and after adjustment. The image on the bottom right is a hyetograph or a mass curve of rainfall through time. So here we can see hourly incremental rainfall accumulation. These are the black bars. Okay, that's hourly incremental rainfall. And then we can see the continual accumulation incremental through time here on this continual chart. And this particular rainfall event, as I mentioned, produced 600 millimeters of rainfall through time. But as I mentioned earlier, it's very important to understand how that rainfall accumulated in time. It didn't just all come in one piece or a nice steady uniform accumulation. You had bursts of rainfall, then dry periods and more bursts and rainfall. And that's really important to capture in the hydrology because that produces a much different runoff scenario than if it just accumulated uniformly through time. Now, once we have these rainfall events identified and then the rainfall quantified in time, space, and magnitude through the SPAS process. For PMP development, we then have to maximize these storms. We have to say, hey, this storm produced 600 millimeters of rainfall. Great. Had everything been perfect, had Mother Nature been perfect when the storm occurred, how much more rainfall could have occurred versus what actually happened? That's the in-place storm maximization process, right? So how do we do that? How do we figure out how much more rainfall the storm could have produced than what was observed? Well, in the PMP process, we make several assumptions because we have a limited data set of observations and we don't know all the answers from observational data. So we assume that these storms already represent maximum or near maximum storm efficiency. In other words, the engine in the atmosphere that takes moisture and converts it to rainfall on the ground. We're assuming that that engine is performing at near or at maximum levels. And therefore, the quantity that we can vary and analyze and compare is the amount of fuel that was available to that storm, the amount of moisture in the atmosphere. And so we can analyze the amount of moisture in the atmosphere and then say, hey, here's how much moisture occurred with this storm. Here's how much more could have happened. And if that had happened, we can make the assumption that the efficiency would be the same, and therefore we would get an X amount more of moisture available. And that's called in-place maximization. So how do we do that? Well, what we do is look at rainfall events that have occurred and try to quantify the moisture that produced the storm. There's lots of tools out there to do this. And in a lot of Southeast Asia, there's a lot of climatologies that have been developed, which are great. But what we need to understand is where the moisture came from that fed the storm, that infected into the storm. So here's an example from the east coast of the United States from a tropical cyclone or hurricane that occurred in the North Carolina and Virginia in September of 1999. And there's a global data set of model reanalysis fields from a trajectory model that's called high split. This is freely available to anybody who wants to use it, or you can enter in your starting point, in this case, the black star, and you can tell it, hey, I want you to go backwards in time, X amount of time, and tell me where that air parcel came from that ended up at my point right here. For consistency, when we do these analyses, and we've done hundreds of them all over the world, we usually go back 3 days in time or 72 hours, and we look at different levels of the atmosphere. Now, that's really important because almost all of the moisture in the atmosphere that produces rainfall is contained in the lowest couple thousand meters of the atmosphere, right? Obviously, if you're starting in high elevations of Nepal, let's say at 2 or 3 or 4,000 meters, there's not nearly as much atmospheric column to work with to produce that rainfall versus if you're starting at sea level in some other parts of the world. But high split doesn't care about that. All it's trying to do is tell you where did the moisture come from that resulted in my rainfall. So in this case, we have a high split trajectory showing a surface line here, this red line, a line here at 850 millibars or about 1,500 meters above the surface. I'm sorry, about 500 meters above the surface, and a green line at 700 millibars or about 1,500 meters above the surface, 3,000 meters above the surface. And what this is showing is that the moisture in this particular case all was originating over the warm ocean waters of the Gulf Stream off the east coast of North America and the Caribbean. And that makes sense. You know, to get heavy rainfall, you would expect that you would need more moisture in the atmosphere than normal. So this moisture was drawing from very warm ocean waters out in this region several days ahead of time, and then moving into their storm center location and producing the heavy rainfall. Now, what do we need to quantify what that means for in-place maximization? So what happens is we plot the sea surface temperatures and surface dew point observations from that same trajectory out where the moisture was advecting into the storm and quantify the temperature at that time. Now, these temperatures are in degrees Fahrenheit, but it's no different than if we did it in dew point in Celsius. And so these values are about 77, 78, 79 degrees Fahrenheit, or about 24, 25, 26 degrees Celsius. And it's very consistent across this whole region. So these are observed sea surface temperatures during the time frame when the high split was saying that the moisture would be moving in from these areas. You can see the high split lines plotted in the background. You can see the sea surface temperatures plotted as well. And this area here is the actual rainfall isohydal patterns that are plotted over the east coast of the United States. So again, we can see our moisture moving in. We can identify the region of interest that's producing the rainfall, the moisture, and that becomes our storm representative location. And in this case, this example, we're using sea surface temperatures because all of the rainfall came from occurred all the way to the coast of the landmass, and therefore we could not use dew point observations because it was contaminated or affected by the rainfall in that area. And so we have to go upstream over sea surface temperatures and use that as a surrogate. So once we have those values identified, basically 77, 78 degrees Fahrenheit, we can then compare that to sea surface temperature climatologies in the area. In this case, we have low 80s for our sea surface temperatures. And that produces a ratio or a maximization factor. So we compare the observed values, mid and upper 70s, to the climatological maximum values in the same area, and we can get our ratio that produces our in-place maximization factor. So in this particular case, the in-place maximization factor is simply a quantification of the amount of precipitable water that's associated with our observed amount. And again, this is in Fahrenheit and inches in this example, but 78 degrees Fahrenheit and 3.29 inches of precipitable water. And that value is derived from the World Meteorological Organization, Annex 1, where they have a table of precipitable water, where you can start at the surface and go all the way to the top of the atmosphere. And you can start with a given temperature and find out what that precipitable water would be based on that observed temperature. Then we do the same thing for the maximization side. So for the climatological maximum side, in that same location, we have a value of 82. And that produces an amount of precipitable water, in this case, 3.95 inches. So comparing 3.29 to 3.95 gives us our in-place maximization ratio of 1.20. So a 20% increase in this particular storm. And again, that can be done anywhere in the world that we have observed data in a climatological data set. That's using sea surface temperatures. Now let's look at the same process using surface-based dew points. Again, this is for a storm in the eastern United States. This is from August of 1969. This is a remnant tropical system that produced intense rainfall, about 30 inches of rainfall in 6 to 12 hours over the topographic and orographic terrain of the Appalachians in Virginia. And we can see, again, we run our high split, we can see that moisture inflow. First starting over the warm Gulf of America and Gulf Stream waters and moving warm air into the southeastern United States. In this case, we have plenty of observations over land to be able to utilize as we go back in time. So now we can do our maximization here using surface dew points. So just as a quick analysis, we can see where the rainfall occurred. This is a SPAS analysis of the total storm rainfall. Heavy rainfall right over the Appalachians there in Virginia. And we can see the rainfall accumulation in time. Again, this is in inches. But 27 inches of rainfall is equivalent to a pretty big event when you talk about 6 to 12 hours of rainfall. You're talking about nearly 700 millimeters of rainfall in just a short amount of time. And you can imagine the flooding and devastation that resulted from that. So when we go to maximize this storm, now we can plot surface-based dew point observations. So each of these is a surface-based observational site during that time in 1969, and we can produce the 24-hour, 6-hour, 12-hour, etc. dew point climatology, either 12-hour persisting or 12-hour, 6-hour, 24-hour average values in the region that was upwind of our rainfall event. Again, our storm center is here. These are the high split trajectories. So we go backwards in time outside of the main area of rainfall, and we quantify the dew point observations that represented the moisture flowing into that storm. And then so once we have that value and that location, now again, we can maximize that amount against the climatology. In this case, we have 77.5 degrees Fahrenheit. And then we take our dew point climatologies that we've developed all over the world, and we can compare that value. So we have our value for July right here and our value for August. And remember, we do this maximization based on when the storm occurred. So in this case, it's middle of August of 1969. Well, the climatological maximum values in this part of the world actually occur in July. And part of the process of in-place maximization is to move 2 weeks towards the warmer season. And so in this case, we move towards the beginning of August, about August 3rd. And so we have to use both July and August as our dew point climatology maximum values, and a percentage of both of those to maximize our storm. Because these climatological maps represent the middle of the month, the 15th of the month. And so we use both pieces of information for that. In this case, it's very similar for the area of maximization in both cases, right about 79 degrees or so. And so again, we go through the same process I showed for the sea surface temperatures. We have our storm representative dew point value here, 77.5. We convert that to an amount of precipitable water. And then we compare that to the climatology, in this case, 79 degrees, which produces 3.44 inches of precipitable water. And we do that simple ratio and get an in-place maximization factor for this storm of 1.07 or 7%. So again, the step is, as we've gotten to this point in the PMP development, understanding the region of interest that we're dealing with, understanding which types of storms produce PMP estimates, identifying the biggest storms that have ever occurred in that region, quantifying the rainfall with those observed storms in time, space, and magnitude, and then maximizing those storms in place. That's where we are right now in the PMP process. So once we've done that, now we have a process that we can start to utilize to develop PMP estimates and understand what those PMP depths are for a given location. So as we go through that process, analyzing those storms and putting those pieces together really helps us reduce risk and uncertainty for our engineering and design analysis. And that's really important when we're trying to understand if we need to resize a spillway or how big to build a spillway, or understand what communities or processes or infrastructure are at risk, and are we appropriately aligned and often dealing with that. So if we can reduce that uncertainty and better quantify the values, we can often reduce costs significantly in this process and reduce risk. Of course, in the process, reducing costs and so on is not the goal. The goal in any PMP development study is to get it right, right? We want to get the values as accurate as possible. In the end, the numbers are what the numbers are if we've done the process right. So getting it right is what matters. And the other parts just come out of that process. Making sure that we document things and appropriately quantify all the decisions and the subjective processes and the uncertainty is really important. And so that can be documented in detail so that a person could come in 5, 10, 20 years from now and understand what was done and why, and improve the process if necessary. Having consistency with past work and current work in the region is very important. That's a big part of the scientific process. Building on what's been done before and improving that is a big aspect, and continuing to do that going forward, of course. And trying to make these processes updatable and accessible. So as I walk through the storms and how we analyze them and how we maximize them and how we move them around, keeping those databases updatable and accessible is really important in the process. Okay, so what I want to talk about real quick is, what does this all look like when we put the pieces together? So I talked about how we understand the meteorology of our region, identify storm events, quantify that rainfall, maximize that rainfall. Well, the last step then is to take that information and move it to our region of interest, combine all those maximized storms together, and see which ones produce the largest rainfall amount over at a given area size at a given duration. And so when we do this on a gridded basis. And that allows us to do a calculation for any location all the way from 1 square kilometer up to thousands of square kilometers, right? And so these are examples of outputs that we've done in different studies. Here we're in the southern United States. This is the state of Texas, the states of Oklahoma, Arkansas, Mississippi, Louisiana. Here's Tennessee. And these are covering thousands of square kilometers, okay? And so what I want to look at is how those outputs come together when we put the pieces together. So in this example, over the entire state of Texas, which is, nearly 500,000 square kilometers. I mean, it's a huge area. We were able to analyze hundreds of storm events in this region and develop PMP, like I just talked about, from the storm-based approach. Now, once we have those values derived, we can look at them by storm type. So this map represents local storm type PMP depths for the 6-hour duration for 10 square miles or about 25 square kilometers. And what we're looking at here is a depth. I know it's hard to read, but these are in inches. But basically, this is ranging from about 250 millimeters up to about 500 millimeters or so across the whole domain. And what you see here is how the PMP depths capture the spatial variability of rainfall in this region, where we have very heavy rainfall and frequent storm events right along the Gulf region here, around Houston and Corpus Christi and so on. And as we move inland towards Dallas and Austin, we still have heavy rainfall, but it's certainly drier. As we get into the western parts of the region, it's much drier. So here we're capturing the spatial variation of PMP accumulation that would occur in the area. In other words, a PMP rainfall event, say around Amarillo, Texas, in northern Texas here, would be much different than a PMP event around Houston, right? And so you want to capture those spatial variations and the differences in magnitude. And you do that by making sure that you've appropriately moved storms around and transpositioned them to the right regions, that you've identified the PMP storm types that occur in your area, that you have quantified the effects of topography and access to moisture and climatology. It's very important. And you see a similar outcome when you look at this map here from Louisiana up through Oklahoma, the very big differences in rainfall accumulation. Here in the Tennessee region, we have the Appalachian Mountains here in eastern Tennessee and western North Carolina. That produces a very different outcome than the plains areas here in western Tennessee. And so we have a wide variety of rainfall accumulations that are affected by the topography here. And of course, you would see the same thing in places in Nepal, where you have very much of a spatial distribution of rainfall based on the topography in the region and how that affects moisture availability, moisture inflow, and storm characteristics. Here's a couple different images of PMP development from some other large regions in the United States. Here is the states of Colorado and New Mexico, where we have the Rocky Mountains, right? So we have topography here that goes up to 2,000, 3,000, 4,000 meters in elevation over very short distances. And in Colorado, the moisture comes in from the east-southeast, this direction over here, and then encounters the high terrain. And so when it does that, you get much higher rainfalls over the plains of Colorado and right along the front range of the mountains or the foothills, just like you would in Nepal. And then much less rainfall as you get inland into the higher elevations in the mountains and valleys. Again, it's very important that your PMP depths capture that spatial variation and properly represent how topography would affect the rainfall. Okay, so once you have those depths, like I mentioned in the PMP process, the next step then is to distribute them temporally and spatially. So this is just an example of a series of temporal patterns that we have developed over the years for our numerous studies through time. And basically, these are different accumulations through time for different storm types. So local storms, which would be thunderstorms and convective systems, and then general storms, which are frontal systems. And these would be similar to what you would expect to occur during the monsoon season. And then you have tropical systems, or for coastal areas that are affected by tropical cyclones and hurricanes. But the bottom line is we have lots of different ways to get from 0 to 1, right? So for local storms, we produce incremental rainfall accumulation in 5-minute and 15-minute time steps through 2 hours and 6 hours, and hourly time steps to 24 hours and so on. So we can figure out how the rainfall accumulates temporally. Now, the point of this is that these patterns are built off of observed storm events. So if, again, just going back to Nepal, you would want to look at how the rainfall accumulated in time from the storms that were used for PMP development and develop temporal patterns specific to your area by storm type. And then as an engineer or a hydrologist, you'd want to apply these different patterns to see which one produces the worst case rainfall accumulation. What do those look like when you plot them and graphically? So for example, here is our 2-hour local storm pattern, this purple line. And you can see how intense the rainfall is over that 2-hour period. Hence, that represents a local storm or a convective storm. And then you can look at the 90th and 10th curve. So the red line is the 90th and the green is the 10th, where you have higher accumulation in the early part of the storm and then it falls off later. In the 10th, you have higher accumulation in the latter part of the storm. And there's several different patterns that you can apply, as I just showed. And that's for the local storm. Here is for a general storm over a 24-hour period. Again, different rainfall accumulation intensities through time. And that makes a difference in how the rainfall runoff and flooding occurs for your basin. But the point of that is to investigate the storm accumulation patterns that you're using for your particular location and develop these patterns based on that information that you have. From a spatial perspective, Again, this also makes a big difference, right? This is a large basin, about 40,000 square kilometer basin in Alabama and Georgia in the southeastern United States, where there's areas of topography here and no topography down here. The pattern on the left shows our gridded PMP depths plot. You can see the grid in the background, and you can see the variation of PMP depths. The blues and the greens are the higher rainfall amounts, and the browns are the lower rainfall amounts. So you can see our highest amounts are closer to the Gulf of America, and then as we move inland, we become lower because we're getting further from our moisture source. And then as we get into the terrain here, we get higher amounts because now topography comes into play and helps to enhance the rainfall. But again, this is a default pattern that's based on, say, frequency climatologies in the background. The rainfall can certainly accumulate in other patterns than the default pattern. And so here's an example of the same basin where the rainfall now is centered over the middle part of the basin and not the southern part. And of course, this makes a big difference in the rainfall runoff patterns and how much rain accumulates and affects a given infrastructure project in this area. So alternative spatial patterns are very important to investigate, especially when you have topography in play. Now, very important in that process is that when you have significant topography, you have to be cognizant that your rainfall patterns, again, have to represent a physically possible outcome. So you would never have the highest rainfall in a protected inland valley, for example. It would always be on the upwind slopes or the foothills upwind where the moisture is interacting, or the higher elevations, for example. Now, another important consideration in areas where you have snow accumulation is how much snow can be available to melt at the same time you're having your heavy rainfall. Of course, this is important for higher elevations in the Himalayas and in lots of different parts of the world where snowfall can be on the ground at the start of a wet season or a rainy period. And this is just an example of how you can develop that. So in this particular imagery, we have a sequence of 100-year snow water equivalent depths at a given time of the year. So this case, this is in the Rocky Mountain regions of Wyoming, Colorado. We have snow water equivalent depth. Again, these are in inches, but this is a high amount of snow available in the mountainous areas at this time of the year. And then we have to melt this snowfall either during our 1, 2, 3, 4-day period of PMP rainfall and accumulate that melt with the observed rainfall. And to do that, we have to have a temperature sequence and other parameters to be able to melt that snow. So in this case, we've identified the amount of snow available to melt and then a temperature sequence over that same domain to see how much snow melts through time. Again, these temperatures are in Fahrenheit, but basically everything that is in the purples and pinks is above freezing. And so those would be areas in here where we'd have melting snowfall. And we can see how that would accumulate and melt through time and then process that amount of melt and combine it with our rainfall in this situation. So here we have different starting dates, March, April, and May, all the way through early June. We can see the amount of snow melt or snow available to melt through time. And starting with those different temperature sequences, we can see how that snow melts through time. Now, if we place our PMP event on top of this, let's say on May 1st, now we have this amount of snow to melt during our PMP event, and those combined rainfall and snow melt amounts could be very important for our PMF, or probable maximum flood, or inflow design flood. So that's why you want to make sure you're considering this appropriately in a place where snow melt is important. Now let's talk about uncertainty. Okay, so we've talked the last 40 minutes or so talking about the deterministic PMP development process, understanding the meteorology and climatology and topography of your region, identifying extreme storm events that can be used to develop your storm database, quantifying that rainfall in time, space, and magnitude, maximizing those events in place, and then moving those events to your location of interest and combining them to get your PMP depths. All of those aspects have a range of uncertainty in those processes. So we want to quantify that when we're doing PMP and see where our best fit values compare to a range of potential outcomes. So as I mentioned, there's several steps in the PMP process, and if we quantify the uncertainty of each of those steps, we can produce a histogram of uncertainty. And in that process, we can plot our deterministic values versus the median and the other ranges. In this particular example, our best fit value is the dotted line here. And we can see how that compares to our 50 percentile or our median estimate. Sorry, those solid lines are best fit. And we can say, hey, our best fit value for this particular basin was 157.4 millimeters in 24 hours. Now, how does that compare to the median? The median here is 179. So in this particular case, our best fit value is slightly skewed towards just below the 50th percentile. But in reality, that's right towards the middle of the range of uncertainty. And that's right where we want to be. That's good, right? If we had our value down to, say, towards the 5th percentile, we'd probably want to take more conservative application into hydrology, maybe add more freeboard and so on. And conversely, if we were at the upper end of the range, we'd probably be okay being less conservative in those applications. The next thing that we want to look at is the probability estimate. As I mentioned, it's a big deal that we've been doing over the last 5 or 10 years, is quantifying the annual exceedance of the PMP in general. And so when we do this is an example from a statewide study in Maryland, where we have hundreds of observational stations that we go ahead and develop at site probability distributions for them and frequency distributions, and then do a regional L moments methodology to combine these station years together to get probability distributions that extend way out to the far end of the spectrum. And to do this, we have two things going on. Combining all the stations together gives us enough data to produce very rare recurrence intervals. And then we have to take these point estimates and distribute them over larger area sizes. And so using the storm database, we can develop error reduction factors and understand how those precip frequency depths would decay through time. Now, what does that look like when we do a regional L moments process? Again, we're now stepping from a deterministic PMP process to a probability spectrum, and we're going to put those two pieces together to understand what the rarity of our PMP is. This is a very straightforward process developed also by the Bureau of Meteorology in Australia and by the Corps of Engineers and Nuclear Regulatory Commission in the US. Very well-known statistical process, but it really is based on the foundation of being able to have enough station data to combine them to station years within homogeneous regions and getting the best goodness of fit probability distributions and putting that information together at site and then scaling it and doing spatial mapping using mean annual maximum values and regional growth curves to get those values you need. And so once you do that, you can distribute those annual exceedance probabilities across your area of interest and get an outcome of AEP of your PMP. In this particular case for the state of Maryland, our PMP recurrence intervals are anywhere from 10 to the minus 6 to 10 to the minus 8, right? So very rare. And that's exactly what we expect our PMP to be, is very rare. And so we can look at these at individual basins and see what that looks like. So in this case, the purple line is a deterministically derived PMP that I talked about earlier. And where that line crosses our probability distribution becomes our annual exceedance probability of that basin. And this is for an 81 square mile or about 300 square kilometer basin. And you can see where those values cross becomes our annual exceedance probability. In this process, we produce a whole table of recurrence intervals all the way from 10 to the minus 1 to 10 to the minus 10. So we can see where our PMP depths fit in with that process and assign that probability. But from this, we also get lots of very valuable information. You know, what does a 10,000 year event look like, or a 500 year or a 100 year? And we can use that for other risk-informed decision makings and lots of other aspects. So combining the deterministic with the probabilistic is a very big step in the PMP processes that have come into play in the last 5 or 10 years and very important in this process. So that's all based on observational data and where we are today. What about when we talk about climate change and how that affects PMP? Where are we going with that? Well, in the process of doing all these PMP studies, we've begun to do climate change assessments associated with them all over the world as well. So we've done hundreds of studies as well that incorporate climate change into these PMP assessments. So we can really evaluate how climate change projections are affecting PMP projections. So how do we do that? Well, of course, we utilize a current suite of climate change projections from the CMIP6 outputs that are part of the IPCC distributions. And we utilize regionally downscaled climate change projections for different emission scenarios. If you're familiar with the climate change processes, they produce a number of different emission scenarios that represent greenhouse gas emissions and societal effects through time, and then try to relate how those greenhouse gas concentrations will affect atmospheric processes through the future, in this case through 2100. In that process, of course, there's a lot of uncertainty, a lot of assumptions, and a lot of scenarios that are applied. What we're trying to do in a climate change assessment is take what-if scenarios, potential outcomes in the future, and compare them to our deterministically derived PMP depths and our probabilistic estimates we just talked about to see if those climate change projections are exceeding the range of uncertainty that's already built into our climate change or into our PMP development processes. When we do this, we generally look at the highest emission scenario, 8.5. This is SSP 8.5, the line here. And the middle of the road emission scenario, SSP 4.5. That basically brackets the most likely outcome with the most unlikely outcome. And so we can kind of see what those range of variances are in those downscaled projections. But as I mentioned, it's very important that you understand climate change projections are just that. They're projections. They're not exact answers. They're what if scenarios. And there's a lot of uncertainty in that process. Of course, there's uncertainty just in the way that we observe data. There's uncertainty in the way that the models replicate the atmospheric processes. There's uncertainty in the way that greenhouse gas emissions might occur through time. All these things have to be considered. And when we do these analyses, we consider that term of uncertainty to be basically an envelope of plus or minus 20%. And so what we're really looking at in these climate change projections is, are we seeing outcomes that are more than plus or minus 20% versus our current observational period? When we do this, we look at the full suite of multi-member model ensembles that are available in the CMIP6 outputs that have the values and parameters that we need. We need temperature, we need precipitation, relative humidity, wind speed, and so on, that are available on a daily time step for our region of interest. Okay, and so once we have that information analyzed and downloaded for our region of interest, we evaluate it in different ways. And what we're hoping is that these different evaluation methodologies all kind of hone in and come out to about the same answer. Okay, so we do a trend analysis. We do a monthly, seasonal, and annual climatology analysis. We do a frequency analysis. And again, if you've seen other climate change work, this is a little different than what you'll see a lot of times from the World Meteorological Organization, because what we are focused on is the parameters related to PMP and extreme precipitation. That's what we care about. And so when we do these analyses, we do them over different time frames: 1 day, 3 day, annual, seasonal. We want to look at different times of the year: summer, winter, all season. If you think about Nepal and those regions, you're talking about very extreme seasonality, where if you just did an annual analysis, you would smooth out some of the variations that might occur in the monsoon season versus a non-rainy season. We look at the historic period and the two emission scenarios that I just mentioned. And when we're doing that, of course, we want to compare what the historic period and the models are saying has happened versus what they predict to happen versus the different emission scenarios. So in the trend analysis, we look at actual data, see what trends have been observed, if any, in the past period, doing a simplified Mann-Kendall statistical test at the 0.05 realm, and see, hey, are we seeing any trends? And then yes or no, we could compare that to the model historical period. Is the model seeing historical trends or not? Because that tells us how well the model has done evaluating the historical period. And of course, if it's doing a good job in the historical period, we'd expect it to do a good job going forward. That's a trend perspective. From a frequency perspective, for each of the 26 models that we look at the range of change and the amount of change through time for each emission scenario for different frequencies of rainfall here and temperature. Here we're looking at precipitation. This is for 1 day for all season, 1 day summer, and 1 day winter. And from a frequency perspective, from the all season perspective, at the middle of the road scenario, 4.5, there really is no change at all. And in fact, a decrease as you get towards the more rare recurrence intervals, 500 and 1,000 years. For the 8.5 scenario, it does show an increase. So quite a difference between the two scenarios. Now, if you look at that by season, though, you have a much different picture. Again, in the summer season, we can call this a monsoon season. Both emission scenarios are showing a pretty decent increase. Okay, so that's important to know, that during your wet season, you might expect to get more rainfall in this particular case. But during your winter season, when it's drier, there isn't nearly as much of a change, right? So if you think about what that could mean for your operations and application, that's important. Now that's at 1 day. So those would be convective events and thunderstorms. If you look at longer duration events, say 3 day, again, we have much less change. Not only that, but importantly, during the summer season, in this particular case, we have a decrease over the 3 day period from our projections. That's, again, very important. Think about what that might mean for your reservoir storage, reservoir operations, your procedures for your hydropower and dam and stuff. So delineating these frequency outcomes from climate change projections over different recurrence intervals over different time frames can provide a very unique picture for each time frame that you can utilize to understand the variances and the nuances in that process. In this case, from an annual perspective, again, basically, this is showing a decrease overall. And again, that would be important. I mean, it's just as important to know if you're going to have less water as it is to know if you're going to have more water, right? So all these things are important in your evaluations. Now, quantifying that range of variance through recurrence intervals is also very important. So in this particular case, in the winter season, you'll notice we're showing an increase through all the 26 models. Box and whisker plots show the median, the 25th, 75th, and the whole range. But then as we get to more rare recurrence intervals, those values begin to decrease quite a bit in the winter season. However, in the summer season, we see more of a steady outcome through time. And then as we get to more rare recurrence intervals, a decrease. Again, having that information by season and how things are changing by various recurrence intervals is very important. Now, what matters in the end is what you can actually use and apply to your project. Right? It's one thing to have climate change projections and have this whole range of outcomes and all these different scenarios, but what you need is something you can actually apply and use, right? What's the most likely outcome? So when we do these climate change assessments, we actually do a whole summary table that shows what is the most likely outcome per emission scenario per parameter. And this is an example of that type of output. So we have temperature here, precipitation frequency values and changes for 1 day, 3 day, and annual, and so on, and for emission scenario. So the 4.5 scenario. Again, remember, we're using a multi-member model ensemble with hundreds of realizations to come up with these range of values. And so when you look at the minimum and maximum, if you just took 1 day summer precipitation, it ranges anywhere from -31 to 134% change. Which one of those do you use, right? That's a huge difference. And so what we look at when we do these multi-member ensembles, the recommendation is always to use the median value. Now, we also have a choice of which emission scenario to use. So we'll look at that as well. But in this case, the median of the 4.5 basically produces almost no change for the summer precipitation for this particular project. And at 3 days, again, we're very close and within that range of uncertainty. Now, the values certainly skew towards the wetter side, so you'd want to take that into consideration and run sensitivities expecting slightly wetter conditions. Under 8.5, really not much difference, also very much within that range of uncertainty, but again, skewed towards the wetter side. So for application, the areas that are outlined in red, these values would be what we would want to apply for a sensitivity evaluation in this particular case. Okay, so it's very important that you actually have something that you can apply from a climate change perspective. You could apply these variances to your PMP depths or to your frequencies of rainfall depths and see if they would change your current infrastructure design or if you're still safe, right? So that's how we put all of these pieces together, right? We want to make sure that our PMP depths are representative of observed storm events, of maximized storm events, of storms that could be transpositioned to our area of interest, and that we've maximized them and grouped them appropriately. And then we've considered how they look from a probability perspective. And then we make sure that we have appropriate temporal and spatial patterns assigned to them. And then we evaluate